Very good morning to you all. Today we are going to see Introduction to Computer Control of Processes Part 5. This our 10th webinar. Yesterday we have seen how to find response for PID controller. Today let us see how to find discrete time response for other systems. If you see the digital control algorithm, if you see the digital control algorithm, it is a discrete system. It is a discrete system. For that, if you give discrete input, it will give discrete output. So how to analyze a digital control algorithm in discrete time system, that we'll see today. And another important component in this direct digital control system is process. The process is a continuous time system. Always process is a continuous time system. But the control algorithm that we have seen today gives discrete output. That's why the discrete output cannot be given directly to this process. That's why we need a hold circuit that converts discrete into continuous, so that the discrete input given to this system will go as a continuous signal, continuous input to that system. But in the external, if you sample that, both sides we have sample. The input is the sampled signal, output also sampled signal. Now we know how to express continuous time domain signal in Laplace domain. We will find is G of S directly. Because the input is continuous, output also continuous. But here the system is continuous. That's why we cannot give discrete input. So a hold circuit is introduced before this process, and the discrete input is given to the hold circuit. That hold circuit converts the discrete into continuous. Therefore, in discrete domain, we cannot see G of S alone. Along with G of S, always a hold circuit will be there. That's why while finding discrete time system, we should consider hold circuit always. Now let us see how to find the transfer function of discrete system. How discrete time system is represented? C of n. C of n means C of nt. That is, the continuous time signal C of t is sampled at nth sampled value. Sampled at nth sampled value. The sampling period is t. That is C of nt. C of nt can be written as C of suffix n. So that is written here. It is function of past values of input error if it is a controller, and past values of output. That is a present value. If you see a second order system, how we will write a mathematical model of second order system? D square y by dt square equal to a dy by dt plus dy plus cu, where u is the input, and dy by dt consists of past values. Y also consists of past values. Let us see now. If dy by dt is what? Change in output, change in the present output from previous output. If it is a discrete system, continuous system, it is dy by dt. If you convert this into discrete system, you will get past value for this, past value for this, present input, like that, to represent this. In discrete time, that's why it can be written as the past values of output, sequence of past values of output, m past values of output, plus k past inputs. If you consider, that is the present value. We will see this by one example. Here at the 0th instant, you are giving input to this system, A impulse input is given. Impulse whose magnitude is C naught. C naught is its magnitude that is given as input. So this hold circuit, what it will do? It will convert this impulse into a rectangular pulse, because its magnitude, it is given like this. This impulse is given at t equal to 0, that is converted into a rectangular pulse. If you give that rectangular pulse, this is the response of that system in the output. Here, if you notice that the input is given at t equal to 0. Input is given at t equal to 0. But the response extends beyond first sample value, t equal to t. After that also, it expands. It means if you give input now, it will persist for long duration. That's why if you want to see the response for present input, some inputs may entered into the system earlier. Those responses must be included in the present value. That's why this is the reason for the mathematical expression is like that. The mathematical expression, the difference equation for that discrete time system is looking like, because of that the discrete difference equation for discrete system is looking like this. Sum of past inputs, sum of past outputs. If you add m past outputs and k past inputs, if you add, you will get the present output. So if you take Laplace, Z transform for this, you will get C of Z equal to A naught E of Z. First term, if you take E and T, if you take Laplace for E is the input, E and tau. For that, if you take Z transform, you will get E of Z. That's all, present value. Suppose if you take Z transform for E of n minus 1 t, for that, if you take Z transform, you will get, it is delayed by one sampling period. Therefore, Z power minus 1 E of Z you will get. So that is written here. Z power minus 1 E of Z. Here K is sampling period delay. That's why AK E of Z power minus K. Similarly, for input also you are writing C of for output also you are writing C of Z past values before 2 sampling period, past values before m sampling period. Like that, if you add all together, and here you can take E of Z outside, input outside. Here C of Z output can be taken outside. Bring all C of Z to the left hand side, E of Z keeping right hand side. You can find the ratio C of Z by E of Z. It is a polynomial of polynomial in terms of Z. This is also polynomial in terms of Z. Denominator and numerator are polynomials. This is the transfer function in discrete system, discrete domain. Transfer function of the given system in discrete domain. C of Z by E of Z. Now, let us find the transfer function for PID controller. If you consider a PID controller in continuous domain, what we will write? We will write Kc m of t equal to, we'll write m of t equal to Kc multiplied by E of t plus Kc by Ti, integral of minus infinity or 0 to infinity E of t dt plus Kc Td dE by dt. This is the expression for PID controller. E of t, if you take Z transform, n sampled value, if you convert this into sampled value, E of t becomes E of nt. E of nt can be written as E of suffix n. The controller output at nth instant is C of nt, that can be written as Cn. Here integration becomes summation. That's why we are integrating this up to present value, up to t, not infinity. It must be t. It must be t. So we have to here up to present value means it must be nt, nth sample instance. So it varies from k to n, e of um, uh, kt, e of kt, as k varies from 0 to n. All past sampled error values are summed up, that is equivalent to integration. But the sample value must be multiplied by sampling period. Then only you will get the area under the graph. So t by ti, here kc by ti, kc is taken common outside. That's why t by ti sigma this. For discrete discrete derivative controller, this is td by t, e of n minus e of n minus 1. So past error, present error, the difference gives equal to d, change in error, divided by sampling period is t, that is taken outside t. In integral mode, we have to multiply by t to find area. Here, to find the difference with respect to time, we have to divide by sampling period. So if you you are getting expression for position form. This is called position form, total controller output. This is the bias value. Now if you write the same for one sampling period before, then this becomes c, instead of c of n, c of n minus 1, instead of e of n, e of n minus 1, instead of integrating up to n, we have to integrate up to n minus 1. Then instead of e of n, e of n minus 1, e of n minus 1, e of n minus 2. Bias value same. If you subtract, let it be 1 and let it be 2. If you subtract first equation, if you subtract second equation from the first, you will get Cn minus Cn minus 1. Right hand side Kc is common, and you have to subtract En minus 1 from En. Plus T by Ti is common. This is integrated up to n. This is integrated up to n minus 1. Therefore, the difference is only last term. That's why that alone E of n came. Here Td by T is common. Here what and all are E of n is there, E of n minus 1 is there. Here 1 E of n minus 1 is there. That's why it becomes 2. This is minus E of n minus 2, because of minus, it becomes plus. So that's all. If you take E of n, if you take Z transform for this, you will get for this C of Z. For this C of Z into Z power minus 1, Kc. For this you will get E of Z, 1 minus Z power minus 1. T by Ti, E of Z. Td by T, this is for this E of Z. Here 2 E of Z, Z power minus 1. Here Z power minus 2. So E of Z can be taken, all E of Z taken outside, bring to the left hand side, you will get C of Z by E of Z equal to Kc. This is the transfer function for digital PID controller. To find the response, step response for this, you can multiply by 1 by Z power minus 1, and you have to find Z inverse. If you find, then you will get controller output at each sampling instant, as n varies from 0 to n, 0 to infinity. Now let us find discrete time response of first order, not system, first order filter. So it is a discrete filter. It is not a continuous time system. It is a discrete filter. It is a discrete system. If it is a discrete system, you can find Z transform without any hesitation. So now you can direct what is that discrete time system? Yn, present sampled value, equal to 1 minus a times past previous sampled value plus present input. So if we take Z transform for this, Y of Z equal to 1 minus a, Y of Z multiplied by Z power minus 1, Z power minus 1, a multiplied by x of Z. If you bring all Y of Z to the left hand side and group, you will get Y of Z by x of Z equal to a upon 1 minus a z power minus 1. This is the transfer function in a pulse, discrete transfer function for the given first order filter. So if you want to find the response for that filter, this is the filter transfer function multiplied by input and find a z inverse. You will get the response. So a by 1 minus a z power minus 1 into input x of z will give y of z. Now if you take z inverse, you will get y0, y1, y2, etc. infinite series by substituting n values, various n values here. On the other hand, if we know these digital filters we have, or n digital filters we have, then these n digital filters can be cascaded together like this. Each one must be a digital filter, digital PID controllers like that. Many digital filters are there. If you know each discrete function, you can cascade like this. You can cascade like this. So cascade of all digital filters finally will give a single digital filter. Suppose this is not digital filter, but it is a continuous time function. Say this is G1 of S, a continuous function. The input must be continuous, output also continuous. This is another G2 of S. This is also continuous function. Then G2 of S. If you find these are all continuous functions cascaded, you know you can cascade continuous blocks in cascade in continuous domain. But if you find the Z transform for each block separately, and you cannot cascade. But each one is a discrete system, then you can cascade. If each one is a continuous system, if you separately finding Z transform and cascade is wrong. What you have to do is, you have to multiply them in continuous domain, G1 of S multiplied by G2 of S multiplied by G3 of S. Like that, you multiply everything together. Suppose 3 systems are there. Then you apply input and find output. If it is continuous, means no problem. Discrete means you cannot give continuous signal as input here. So add a 0 order hold before that and find Z transform for the whole, not separately. If you find separate D, Z, G, Z, and if you put here, it's wrong. When we can put like that, each one is a discrete system. In other words, that can be easily says if it is, this is a discrete system, this is also a discrete system, its output, input is discrete, output is discrete, that can be directly given here as input. Suppose this is continuous system, means here its output is continuous output. How it can be given to a how continuous output can be given to a given as a discrete input to the continuous system? That's not possible. So if all are continuous system, then there will be samplers in between. That's why after that sampler, then hold circuit will be there. That way we have to then only we can find a separate Z transform and you can cascade. Otherwise, if all continuous system means you have to multiply all together in S domain, then you have to find. You cannot find a separate Z transform if it is a continuous system. Each one is a continuous system. Each one is a discrete system. You can multiply. This is discrete transfer function matrix for MIMO system. If let us assume that it is a 2 by 2 system, then this represents for a discrete input M1, E1 is given. For that it gives C1. The same gives C2 also through D21, through this D21. And this M2 is given here. M2 gives C2. This M2 also gives C1 also. So like that. So we can put the blocks this way. So if you give E1, E2 as input, it affects both outputs, similar to a continuous MIMO system. Uh, Now let us find the pulse transfer function of a continuous system. Earlier we have seen pulse transfer function of discrete system. Here we are going to find pulse transfer function of a continuous system. It is a continuous system. It is a continuous system. It is a continuous system. For that, you cannot give discrete input. You cannot give discrete input. That's why this discrete input must be converted into continuous one. For that, this hold circuit is there. That's why if you want to find the why it is called pulse transfer function, because the inputs are pulses. For that pulses, how that system response is called. For that, if you find Z transform of output by input, then it is called pulse transfer function. There is transfer function for pulse input. So the hold circuit process, always the hold circuit must preside over this continuous time system if it is a digital input. Therefore, if it is a continuous time system, we cannot find GP of Z. We cannot find GP of Z. Instead, we can find only HGP of Z. HGP of Z only we can find. That is called the pulse transfer function. Now let us let us see how to find the pulse transfer function for this continuous time system. Now a step input I am giving. Let us assume that I am giving a step input. How I will give step input? At C0 I will give 1. At C2 I will give 1. I'll C3 I will give 1. At C4 I will give 1. Like that I will give a continuous pulses. Suppose I want to see the response at T, at kth sampling instant. I want to find, this is the kth sampling instant, what is the response of the system. Already I have seen that even if you give at t equal to 0 input, its response elapses after some time. That's why some response for this first input also is available here. That's why all these values are added together to find the transfer function. This is the step input. For that you want to find means that t equal to 0, the magnitude of this impulse is C naught. Therefore, if you take Laplace transform of this, you will get C naught multiplied by 1. Because how we will write this impulse? Its magnitude is E of naught into del of t. Like that we will write. So if you take Laplace transform, what you will get? C naught C naught multiplied by 1 you will get. If you give the second pulse is given at first sample, that is t, at t you will get, then here you will get C of t. Here you will get C of t, first sample. N equal to 1, if you put this is the magnitude at second sampling. After that, next sample will be at 2t. Here you will get C naught of 2t, that is the magnitude, multiplied by 1. The impulse is always delayed by t minus nt. If n varies from 0 to infinity, you will get infinite values. We have to add the response of each and every one to get the final response. Now let us find the response of the system for input given at t equal to 0. Well, that is y naught. That is y naught. Y naught equal to h of s hold circuit gp of s multiplied by Laplace transform of c of 0. That is c naught. Laplace transform c of s, already we have seen that. That is c naught. Therefore, y naught equal to h of s gp of s c naught. So what is y naught of t? You have to take Laplace inverse of this, Laplace inverse of HGP of S C naught. So let us assume that this is a response of the system. Then what is The transfer function of the system g of t equal to Laplace inverse of h of s gp of s. What is Laplace inverse for this? That is g of t. That is g of t. So we can write the response y naught of t equal to g of t multiplied by c naught. C naught is the magnitude of the impulse given at t equal to 0. This is the response for the input given at t equal to 0. Similarly, if you give input at c of t, c of 2t, etc., like that, if you give the sampling instants are t equal to t, t equal to 2t, etc. So, what is the response? Y of t minus t. T first at first sampling instant, that is when n equal to 1, this is the input to the system. Therefore, this is delayed by one sampling period. Therefore, y of t minus tau, g of t minus tau into c of tau. So, at the second sampling instant, this is the output. Like that, if you add all together, uh, we are finding the response of the system at t we are finding. So whatever input we gave before this, all must be added together. That's why y of t equal to y naught of t, y1 of t minus tau, y2 of t minus 2 tau, etc. This y of t is here. So all the responses are added together. All the responses are g of t c naught, g of t minus tau c naught, c of t, g of t minus 2t minus c of 2t. Like that, all responses are added together. Then you will get the final response. Then what is that? Y of kt equal to kth sampling instant, the value kt equal to wherever you find t, it must be replaced by t, because yt equal to what we got? Yt equal to sigma n equal to 0 to infinity g of t minus nt delay by nth sampling instant multiplied by c of nt. This is the response for given input c of t. C of t is the input. For that, this is the response. What is the response at kth sampling instant? Sample this at kth instant, you will get this. You will get this. At the same is sampled at kth instant. You'll get y of kt equal to, instead of t, you would put kt. That's all the same. Now let us find z transform for this. Z transform for this. What is that? Y of z. If you take z transform, y of z equal to, what is the definition for z transform? Y of z equal to sigma k equal to 0 to infinity. Y of kt z power minus k, as k varies from 0 to infinity. That is the definition. By using that definition, we can write y of z equal to sigma k equal to 0 to infinity. You substitute now y of kt here, y of kt. This y of kt is substituted here, y of kt is substituted here. Then z power minus k, z power minus k, y of z. Now we can substitute. If you take this t outside, you will get k minus n. Let us assume that k minus n equal to L. If you put, then the equation becomes y of z equal to k equal to what is the value of k? K equal to L plus n. L plus n. Substitute n equal to 0 here. N equal to 0 here. K becomes L. Sorry, L becomes k minus k. So for negative values of L, this becomes negative values of L, this becomes 0. We are substituting k minus n equal to L. Therefore, the index is changing now. The index is changing now. The index is changing now. L equal to k minus n. Here k minus n becomes L. That's all. Now this k has to be changed. This k has to be changed because of this. So so um, what is the expression? L equal to k minus n. Here earlier, what is the value here for k? K equal to 0. You substitute k equal to 0 here. So the L now starts from minus n. Now L starts here from minus n. But we know that the system has values when L is less than 0. That's why this L can be replaced here by a 0. But mathematically it becomes minus n. After that it becomes 0. Similarly, this index, what happens to this? This is n equal to 0 to infinity. That remains as such. That's all. So this k minus n becomes L, C of nt z power minus k. So from this we can find L equal to k minus n. We substituted k minus n. Therefore k equal to L plus n minus k equal to minus L minus n. So minus L minus n is substituted. You can now separate all L's together and all N's together. So if you separate like that, because this is independent of n, this is independent of L. So we are grouping this two groups. One is independent of L. This is independent of L. This is independent of n. So sigma L equal to 0 to infinity. Why we are making L equal to 0 now? Because G of LT equal to 0 for assuming that when L less than 0, this is 0. That's why instead of starting from minus n, we can put 0 to infinity G of L tau multiplied by z power minus L sigma n equal to 0 to infinity C of nt z power minus n. So this is nothing but C of z, C of z. This is nothing but G of z. So therefore, G of z multiplied by C of z can be written as y of z by the output y of z by C of z equal to G of z. That's what we got. So if you want to find the response, then you have to find Z inverse for this by multiplying by this input. This is Z transform or vary function to find the responses as well as pulse transfer functions. This table will be very much useful. That's why it's given here. Now let us find the discrete time transfer function of various systems. First, let us find the discrete time system, discrete time transfer function of integrator, pure integrator. What is the transfer Laplace transform of integrator? 1 by s. Suppose the integrator has a gain of kp, then kp by s. That is the transfer function in s domain. But this is a continuous time system. You cannot give discrete input here. That's why a hold circuit is added before that. Here you can give discrete input. Here, if you sample that, you will get discrete output. Therefore, now we can find Z transform for this. So, if it is continuous time system, definitely we must preside by a hold circuit, because to convert impulse into continuous time signal. Therefore, this hold circuit is H, and the transfer function of this is GP. That's why GP of Z. That is, if you multiply these two together before taking Z transform. Here you should not take Z transform for hold circuit separately, Z transform for integrator separately. If you multiply, then it is wrong, because if you take Z transform for a system, means its input is discrete, output also discrete. You note here that the input to this system is continuous, output also continuous, but a sampler is included here. That's why it is discrete. But input is continuous. That's why you cannot take Z transform for this. If you take this, its input is discrete, If you sample here, then you can find separately. Here it is not sampled, directly given to the controller. That's why you cannot find Z transform for this hold circuit also. Now let us find. It is multiplied by a hold circuit transfer function. We know that Laplace transform of hold circuit is 1 minus e power minus ts, delay by one sampling period, by s. If you find the z transform for this 1 minus e power minus ts, delay by one sampling period, 1 minus z power minus 1, that can be immediately written as z transform. If you write like that, the remaining terms are what? Kp by s square. Kp by s square. Here, if you here it is taken like this: 1 minus e power minus ts, ts divided by s square. S square. This taken separately and this taken separately. That's what here you got. So if you take both common term, if you take kp by s square is the common term, here you will get 1, here 1 minus ts, e minus ts, that is 1 minus z power minus 1. If you find 1 by s square inverse z transform, what you will get is kp t z power minus 1 divided by 1 minus z power minus 1 whole square. You will get kp t z power minus 1 divided by 1 minus z power minus 1. Pure integrator, we got the transfer function is kp t z power minus 1 1 by z power minus 1. That is the transfer function we got. How to find the response for that? Let us assume that for a step input, what is the response? Therefore, y of z equal to hgp of z multiplied by c of z. Hgp of z is this multiplied by step input. You will get this. For this, what is the response? You go to here. This is the response we got. What is that? E power 80. So the response is e power 80. It is continuously increasing function. We got the values at every sampled instant. It goes up to infinity. So what is the final steady state value? This is the system. For that, what is the final steady state? Y of z equal to what? Y of z equal to this 1 by 1 minus z square whole square. So for that, y of z, we have to find y of infinity. Y of infinity. So what is the final value there? 1 minus z power minus 1 y of z. Y of z is 1 minus z square whole square. Now substitute z equal to 1. Kt, this also becomes 1. This 1 means this becomes 0. So something divided by 0 is infinity. So we got final value from final value theorem. And from the response also shows that it goes towards infinity. Now let us find the step response of first order system. Here also it is a continuous time system. It is continuous time system. It is a continuous time system. We cannot give impulse input directly to that. That's why a hold circuit is added before that. The hold circuit will receive impulse pulse inputs. Therefore, we have to find the pulse transfer function by including this hold circuit. In the next class, we will see that without hold circuit, if we give the pulses directly to that system and find pulse transfer function, what will happen to the system? We'll see in the next class. It will be very interesting. From that, we can understand that what is the purpose of hold circuit. We can understand. Here, the hold circuit is included here because we cannot give impulse inputs here. So hold circuit converts that impulse inputs into continuous. That here, if you take Laplace z transform for this 1 minus z power minus 1, so it is at a unit delay. That's why if you bring that outside, you will get 1 minus z power minus 1 z transform of remaining terms kp divided upon s multiplied by tau s plus 1. So if you do the partial fraction for that, 1 by s and 1 by s plus 1 by tp. Here 1 by tp you will get. This is partial fraction is done. If you find z transform for each, you will get for this 1 by 1 minus z power minus 1. For this it is 1 by 1 minus e power t by tau p z power minus 1 you will get. If you substitute these two in the here, you will get this is the transfer function. If you take LCM, these two getting cancelled, and you will get this is the final transfer function of first order system. So HGP of Z for the first order system is Kp 1 minus e power t by tau p Z power minus 1 upon 1 minus 1 minus e power minus t by tau Z power minus 1. This is the pulse transfer function for the first order system. Um, I want to find the step response for that first order system. I have to multiply by step input for that pulse transfer function we got. So do partial fraction, and apply inverse Z transform. You will get for this Kp into 1 by 1 minus Z power minus 1 is 1. Kp is taken outside. For this, it is e power minus t by tau p. So multiplied by n. So as n varies from n 0 to infinity, you will get many values. If you plot all these here, you will get the response of the system. In discrete domain, you will get the sample values only. We got sample values. The what is the final value? For that, we can apply final value theorem. T tends to infinity, y of t equal to limit z tends to 1, 1 minus z power minus 1 into y of z. Y of z, what we got? This is y of z. Y of z you put here 1 minus z power minus 1 and multiply. Here 1 minus z minus 1, that is here. The remaining terms here. These two getting cancelled. And if you put z equal to 1, this becomes 1. If you put this also becomes 1, and these two are getting cancelled. The remaining thing is kp. Therefore, the final value is kp. It will settle at kp. It will settle at kp. So, limit t tends to infinity, y of t equal to kp. That you got. If two first order systems are cascaded, then what you have to do? This is also continuous time system. That's why you cannot give impulse inputs here. So multiplied by zero order fold. There are 3 terms in the denominator, 3 factors in the denominator. Do partial fraction, you will get 3 residue terms. You will get 3. So do take Z transform for each separately. You will get the pulse transfer function for this system. Tomorrow, let us see what will happen if we take a pulse transfer function without adding this zero order fold. Thank you.